This is project simulation for power integrity optimization using decoupling capacitors. So we are using a PowerSI tool and we'll design a 5-layer board with one power plane and one ground plane. We have a certain layer stack which has 2 planes added inside it with a pad stack and other parameters as per design document. In the PowerSI, as we have layout setup, simulation setup on the left, we create a new project. On the right, we have component management, layer selection and net management. This is a layer stack where we have added plane 1 and plane 2 already with the ER of 4.5 set on all layers, and all the fields are editable there. On the pad stack, I can also see the wire diameter of 0.4, pad diameter of 0.5 and anti-pad diameter of 0.6. We classify both the planes as VDD as power nets as well as ground nets on the right in the layer selection. Also going to the box of plane size, we have 150 by 150 mm set as per design document for both the planes. Going to the option, we are enabling all the grids as X and Y grid as 1 mm each. We have nodes and vias added. All the nodes are set up as per X and Y axis so that they are aligning with each other. There are decaps added as well. Vias are added by the add via feature, and then we are having a noise coupling analysis. We have added the excitations of sync 1, sync 2, the RT, and the decaps are already added. The decaps are disabled right now. The simulation runs. We can clearly see local peaks near the sync location. These are noise hotspots where the PDN resonates. Where I enable the show peak animation over frequency, the voltage ranges from 2.4 volts up to around 11.3 volts. The cavity between the power and the ground planes can ring up to several volts. So for both the syncs, we have around 110 megahertz to 2 volts and 500 megahertz reaching almost 8 volts. Now we enable the decap and rerun the simulation based on the hotspots. Now the voltage ranges from about 3.9 millivolts to 558 millivolts. The surface is smoother and the sharp spikes around the sinks are noticeably reduced. The voltage range has dropped from earlier to roughly 154 millivolts to about 1.5 volts. If we compare the spatial mode curves before and after decoupling, first resonance around 110 megahertz is slightly reduced, but the biggest change is at second resonance. So we are going to the model extraction feature right now, and then we go to the setup and we add 2 ports, port 1 and port 2. We hook up the main S1 and S2 to the positive terminal and the negative terminal, and then after hooking up, we disable the decoupling capacitors again because we want to analyze before and after. We are now unticking the decaps and then we start the simulation. After that, there is a strong impedance peak of around 10 ohms, around 100 megahertz, and another peak about 10 ohms near 500 megahertz, separated by deep anti-resonance dips. Now I enable all the decaps again and restart the simulation. After starting the simulation, we can observe in the Z parameters. Now there is some flattened strips. Finally, this graph overlays the extraction results with and without decaps. Around 100 megahertz, the impedance peak is pulled down and around 10 ohms to well below 1 ohm. Near 500 megahertz, the largest peak is also flattened to just a few ohms. Now we can see the comparison for both. Overall, the PDN impedance with decaps is much lower and more controlled.